my research, what we have been doing it for the last 10 years, at least in perovskite solar cells. So that's why I know in photoplat, you guys may be on the silicon side, but I believe that there's a room for new technology to enter in the market, especially in the thin film form. And slowly, we will also want to grow as silicon photovoltaic has achieved the market compatibility. So this is the lab size cells we make every time, 400, 300 devices per week. Sometimes we also make large devices of 10 by 10 centimeters, and to see the efficiency and the performance reliability of them. Today, for the last 2 years almost, we are going through an unprecedented time. And we don't want to repeat this in the term of the climate crisis. Because if we will not act, there will be another disaster scenario in the coming 5 years or 10 years. So I will give you a talk, and that's why Europe has targeted to be carbon neutral by 2050. And these many new technologies will be entering the market. And especially in the last 2 months, you know that we have been facing another problems in our Europe with the electricity price going up. So we need to be self-dependent and self-reliable for the security. So this is the outlook of my talk today. I will give you a flavor about thin film PV, perovskites as a light harvester, different type of thing, and how you replace 2D materials here inside as an interlayer. And then we talk about selective layers, different type, N-type and P-type selective layers. And this is not only a technology photovoltaic need, because we are only educating young generation, inspiring them to think about it, and we are connecting people. So this emerging photovoltaic technology or thin film photovoltaic, apart from technology, we are addressing the most pressing challenges like the climate crisis, and also we are educating the young generation for this one. Cell, a British company, which I think 2020 built up in a sky scenario. And a sky scenario because Europe want to be 2050, some country would want before then 2040 to be carbon, 2040 to be carbon neutral. So we need a scenario. We need to put our milestones on how we are going to achieve it. So in 2015, we signed the Paris Agreement, and we agreed that 2 degrees was too much. So we agreed that 1.5 degrees centigrade, we will cap it. And today we are here, 2022. Some of the cars are running on hydrogen, but by 2035, almost we will be giving more to the photovoltaics, and wind will be our main source of energy. Almost 1/3 of the electricity will come from wind and solar. And slowly this hydrogen will also enter in the market. And by doing so, Europe will be here by 2040, 2050 carbon neutral, but most of the planet by 2070, almost all of the planet will be carbon neutral. And this photovoltaic has a huge role to play. By 2050, most of the things will be done on the photovoltaics. And then hydrogen will be a new vector for long-term trucks and buses. We are very happy with what happened in the last 10 years, the photovoltaic deployment with the silicon. But what we believe that is not optimum. We need 1,000 times more photovoltaic deployment in order to achieve carbon neutrality. So for this, we need a new technology. We need new approaches. We need changing the paradigm shift to approach these things there. I told you as today, the photovoltaic, if you look at here, the solar is almost 5% to 3% here. By 2070, 32% of the electricity, 1/3 of the electricity will come from photovoltaics. 1/3 of the electricity will come from, by 2070, will come from photovoltaic. How this will happen, you can see gradually manner. This is the pie chart. By 2025, 2035, 2075, and 2021, almost 2/3 of electricity will come from photovoltaics. So slowly, this will increase the pie chart, and the market share of photovoltaics will increase. So we are very happy today. The cost of the silicon is very less. Extremely that we are fortunate that now the new installation of a photo energy is much cheaper than burning the fossil fuels in terms of photovoltaics, and of course in some area where the wind, because this is the best gift to humanity. Sun is always shining somewhere, wind is also blowing somewhere. We just need an approach and technology to harvest this technology for a thing fun. Since we believe that perovskite solar cells is targeted to capture thin film market. Silicon is a fantastic product. We don't want to disturb it. Let it there, but there's a room for, we want a parallel entry to another thin film market. There is the CIGS technology, cadmium telluride, now emerging solar cells like OPV and PV. The perovskite solar cells are the most competitive to cadmium telluride because cadmium telluride has the lowest LCOE, levelized cost of electricity. And silicon has not the lowest cost of electricity. Just for your information, is the price is cheap, but the technology is a bit costly. The cost of perovskite is will be cheaper than cadmium telluride. Cadmium telluride is cheaper than silicon here. If the NREL calculated, it will be less than 20 cent watt per peak in comparison to 45 watts per peak for cadmium telluride technology. Why it happened? Because we use less material and we use very low processing cost equipment. Just to give you a flavor, silicon is 200 to 300 micron. Thin film technology is 3 micron. Perovskite solar cells with active material is 400 nanometers, an order of magnitude lower. And this order of magnitude lower will bring down the cost. In terms of processability, silicon, you need them to heat them at 1400 degrees centigrade because you need 99.999959 purity. And perovskite is a semiconductor. We don't need such a high temperature in annealing. So all these things will reduce the cost of the material. If you look at the energy payback time, the energy payback time, of course, this is a difference from area to area. In north of Europe, it will be different. In south of the Europe, where there's a more sun, it will be lower. But just to give you a relative comparison, is crystalline silicon, then polycrystalline silicon ribbon. It is the lowest for organic photovoltaic and lowest for perovskite solar cells. Due to the material usage, the energy payback time will be less because the thickness of the material used and energy consumed during the fabrication of this process. The titanium dioxide is a very good photocatalytic and semiconductor material which need to be annealed at 450 degrees to convert from one phase to another phase. But if you look for tin oxide and other type of N-type material, the energy payback time will be even lower because we don't need high temperature annealing. This is very good at to anneal them at 100 degrees centigrade. And this is, I think, how Europe will generate electricity and how Europe will transmit the electricity. If you look at here, we are here, and almost 2030, by 2022, a very small portion of electricity come from photovoltaic. And we are fortunate that we are in the Spain, where we have plenty of sun, sand, and science. We can do that. And if you look at it, this will be gradually increased. In the case of Spain, it will be if you look at the chart, the green chart area will be rapidly increasing. And that's why by 2050, we will be having fossil energy coming from the photovoltaics. In terms of Europe, Spain, you will see most of them is the PV. In UK, is the wind and offshore wind and the solar PV and hydro. Here in Germany, but in Spain and Italy, we'll see most of their city will come from PV because we are very fortunate to have the sun. And by 2050, this is a scenario for the Spain. It will be most of the electricity, almost 90% electricity will be coming. But we need an approach just to think about it. We need to, how we can do that. So what we needed, we need to, what is our requirement? Our requirement is there's a growing need for high performance PV. High efficiency, which can give you high efficiency, not like 10% and 12%. We need almost more than 20% to 25%. And low material usage. You should have a flexibility and with added benefit of aesthetic benefits, which will have a lowest leveraged cost of electricity, what you call LCOE, life cycle of 25 years of guarantee. The silicon currently give you as a guarantee of 25 years, but of course the performance decreases 7 to 8% year by year. And for this, we have to take the risk and we have to bring new technology in the market. What will be our aid? What will be our strategy? We have to think beyond the silicon. We have to think beyond silicon. We have to think about also in holistic manners, because not only photovoltaic in the sun, but all the sensors, because this is the Internet of Things and BIPV. If we can integrate in all the sensors with the photovoltaic unit, because they can, most of these emerging photovoltaic harvest natural, artificial light. So if they can harvest those ones, so we have also Internet of Things, BIPV. So we have to make a synergy with these things. Minimize the supply chain, because now silicon is being manufactured in Asian countries and come back to Europe. So this is also a big supply chain. It also costs the cost of manufacturing and cost of the product. So if we can locally produce them, and ideally it should cost less than 20 cent watt per peak for a large scale deployment. What we can do, we can set a medium term goal to how we can associate with the clean ecosystem. And then in the long term, we can also make a framework with cooperation with niche application like greenhouses. Means we have also done many experiments, and we have found that the plants grow faster, and the red light and blue light. And red light, there are many semiconductors, otherwise perovskite or organic solar cells, you can provide them a red light. So plant grows 2 times to 3 times faster. So all these things are also very good for greenhouse applications. And apart from this growth of the plant, the greenhouse will be self-sustainable. So you don't need to be provide electricity to them. This wise to a time if I will take you means where we are. So this is if we have a silicon, as we call the first generation or first generation product. And then there's the 3-5 semiconductor, which is also very good, very efficient, but costly also for niche application like in this case. Then in 80s, it comes the thin film. And then thin film is CIGS technology, which is also very efficient, 22.5%. But we have indium, and indium is a very costly material. And the thickness of the material in this thin film is 2 to 3 micron. So indium constitutes a large cost, and it cannot compete with the current silicon technology. So if you replace indium with copper and zinc, so you have a CZTS, and CZTS is the castorized, so this gives you efficiency of almost 12% to 13% in the lab. And so because there's a lot of defect and recombination factors there, and these is not improving for us. Then in the third generation is the emerging photovoltaic or nanostructured photovoltaic, how you call it. So there are many technologies which have been working for the last 25 years. There's organic photovoltaic, disensitized solar cells. There is the facade and EPFL. This is the flexible organic solar cells. And for the last 10 years, almost we have a perovskite solar cells. We are working the last 10 years on the perovskite solar cells because this is also very efficient. Almost 25% efficiency has been reported in the labs. So this is the business as usual. We can leave them to prolong the curve, to learn more, the learning curve, adaptation period for this silicon technology. But we need to take the risk for embryonic technology, and we have to take the risk among the technology which can revolutionize the market here, which has the ability for any photoactive material which can at least produce more than 50% or 20% efficiency in thin film form. This will be very ideal scenario. Just to give you another roadmap about what is happening today in the term of photovoltaic technology, silicon is almost market penetration has done very well. It's also entry is reaching to maturity, but we need more deployment. I don't know how the community will react if we need, because our requirement is 1,000 times more photovoltaic than currently we have it. I don't know if silicon is capable of giving such supply chain, or if the price will be increased. Then we have a silicon of advanced silicon. These are market penetrations already taking. In thin film, many technologies are ready, but due to the cost, they are not able to take a market maturity. They have penetrated some market like CIGS is the market entry, but it's not going inside the market. Cadmium telluride is a very good product. It's also cheap, 22.5% efficiency. But there's only one company, the First Solar, which make it. And then they have already achieved their target, and there's because First Solar has an exclusive right to buy tellurium, and no other company can do that. So this is already a market penetration, and they cannot produce much. Amorphous silicon, which is also 10 to 12% efficiency given. If we're good about the emerging topics, we have a disensitized solar cells. The research has been done for 2-3 decades. They can also give you a performance of 14% to 13%, but they are very colorful. So you can think about window applications. And then we have a perovskites which give you 25%. This is also I put in the red because we are not that stable as compared to silicon, etc. And then we have also organic polymers thing, organic solar cells, which are also very efficient, almost 20% efficiency. You can get it, and the device thickness will be less than 100 nanometers. So perovskite, I think, is the only thin film technology which can compete with the cost and the efficiency to bring down the LCOE. Is also a thin film technology which has the capability to go beyond the Stokely-Kastler limit. The Stokely-Kastler limit is 32.6%. So if currently we have a 25%, the tandem of perovskite is almost 30% has been reported. So what we believe is in coming years and coming couple of years, this performance can be achieved. And this is another thin film technology which can go to mass scale also to compare to silicon. What silicon today is, we are very happy with this, but it took 6 decades, 60 years to achieve this performance. The first silicon was in 1954 in a Bell lab. At that time, it was only 5 to 6% efficient. So 20%, 20 watt module will be like this size. Then by 2020, we have one module is like 320 watts. 1 meter by 1 meter. It is almost 20 to 25% efficient, and we are already producing more than 600 gigawatts. There's one here. And we also have a cadmium telluride, CHS, but these are also in the technology which is waiting at the market entry, but very difficult to say that it will penetrate the market, will achieve full market penetration or not. And by 2050, if we can, all this technology can bring down the cost, like we also need a contribution from silicon, cadmium telluride, CIGS, CDTS, perovskite, tandem perovskite, OPV. So if all these technology or some of them can compete, then we can achieve the 500 gigawatt of installation, and we can push the performance to a 40% efficiency. So why we are doing it? So if I plot some of the thin film technology here, then you will see this perovskite has risen like a rocket. As you can see the red colors here. Just in 2012, it was 3.8% because what we learned is knowledge from the liquid state disensitized solar cells. It was, and then we replaced the liquid with a solid. It was a history from 2012, and then from mere 10%, it achieved to 25.5% efficiency. Organic solar cells has also shown great performance in this last couple of years. Now almost 19% to 20% efficiency is being measured here. Amorphous silicon is the flat 14%. And if you look for other technology, DSA is also not shown much improvement in the last 10 years. If you look for the silicon, there is no improvement in terms of efficiency. The cost has gone down. But if you look for the efficiency chart, this is almost relatively small. This is the castride, the yellow orange color is castride, is 12.6%. So for the perovskite, what we have is low cost, high efficiency. What the missing link is the stability, because we are not 25 years stable as compared to silicon or other thin film technology. So what is missing is the stability, so to finish the golden triangle. Also, we have some problem inside of the perovskite. I think the phase transformation, halide segregation, because we were very happy we took mixed halide, and we were very happy on mixed halide giving very high performance, but mixed halide also has a problem with the phase segregation. Ion migration, crystal size expansion, because when under a stress condition or light, the crystal size expands and contracts. And if you take a mixed halide, then you have a high band gap and low band gap dominant. The pure methyl ammonium lead iodide is a dark color, but if you check iodide with the bromide, it became yellow color and orange color. This is also good for orange colors for BIPV application. You can put them here on your window application, etc. Because they are very semi-transparent. They give you efficiency of 10 to 12% here. Why we think that perovskite is a very good semiconductor, apart from its very high tolerance, defect tolerance, because defect tolerance is very high. We don't need like 99.59 purity like we do with silicon, but defect tolerance is very high. So this is very, you can even just do a spin coater. You don't need a very high energy extensive process to do that. You can just spin coat them and bed them. But also this is the defect tolerance is high, but also the losses are very less. So gallium arsenide is a very good semiconductor. The band gap is 1.43. The loss is 0.3 electron volt. Okay, 0.3 volt, 300 millivolt. Similar, silicon also has a 300 millivolt. And this is the same line with like of perovskite. It also shows a 350 millivolt losses here. In terms of cadmium telluride is very high. Castride is very high because the castride, the voltage is only 600 millivolts, 580 millivolts you can achieve. The losses is very high. So all these things will make it, the energy loss is very high. So this is the band gap, this is the VOC you can achieve, even higher VOC has been achieved. So losses are very low, and due to low losses, it can go to, and you can perform a high devices. As I said that the perovskite is a light harvester material, is a thickness of almost 400 to 600 nanometers, the sandwich between two type of charge selective contact, N type and P type. And then we finish the device with a metallic contact, which is a gold or silver or any metallic contact to do that. This is a perovskite which absorb a light and dissociate and generate electron and hole pairs. And the electron and hole pairs then they travel to their respective electrode. And to harvest the light effectively, we put additional layer of here whole transport layer. On the bottom, we took electron transport layers. And this is the cross-section diagram of a device. This is the cartoon. You can see the same process, just mimic here. The hole will go to the charge collective side. The electron will go to the bottom electrode, and they absorb electrons. So different type of device architecture also you can make it. I don't want to go on that one, like NIP, planar. You can even get rid of mesoporous TiO2. You can take planar SNO2, right? And there's also inverted devices we call PIN. So you start with deposition of a P layer, then you deposit perovskite layer, and then finish device by electron transport N type of layer. And this is good, you can do that. Another thing is that perovskite is a very good absorbing in a visible part of the spectrum. And silicon, very it absorbs from NIR region. So it also gives us an opportunity to make a tandem devices. And tandem devices, which I just commented about, have shown almost 30% power conversion efficiency. So much higher than silicon. Silicon is 26.5 now. So the tandem devices has shown very high. So if here you will see this the wavelength here, we absorb very well in the UV visible level 800 nanometer. From 800 to 1200 or more than that, the silicon solar cells, the bottom cell can absorb. So if you shine a light, perovskite solar cell can be top cells, it absorb the light. The bottom can be silicon cell, and by doing so, you can see our voltage increases, the current is also here, and then we have almost 30% efficiency. Has been people have been reported it. Top cell and bottom cell. It's called tandem approach. But I'm a little bit, I will wait for some time. It's a two-way sword because silicon is 25 years stable, and silicon and perovskite is not that stable. So I will a little bit wait for it for this technology to be do that tandem approach. Rather, I will say perovskite tandem can be also a good approach because recently I think 26.5% have been demonstrated with perovskite tandem. What my lab is doing, we work on a full value chain in a holistic manner. We develop different type of compositional engineering of perovskite, and the perovskite crystals are very large, and sometimes they have a defect. They're very polar, so we passivate them with molecules to make them to create very good interface. We develop different type of P type of L type, what we call electron and hole transport material. We develop different type of doping strategy, interfacial material, hydrophobic doping. All these things will allow us to make a improved reliability, performance, as well as stability of the perovskite solar cell. And we have been working on in different direction on this type of a thing. What my lab is doing, and why most of the people is interested, is doing solution process that the cost can be low. But there's another school of thought, and it's also very good. We can evaporate the perovskite. We can sublime it. You can evaporate perovskite thickness, and this is also very good because if you will evaporate the perovskite, you can exactly control the thickness. You can exactly control the thickness. The device reproducibility will be very, very higher. In wet chemistry technique, we cannot exactly control to 2 nanometer resolution of the thickness. So this is what we do is solution process, one-step deposition, two-step, or different type of solvent engineering approach, or slot die coating, Dr. blade coating. But how there's also good approach of doing with the thermal evaporation. You can do sequential deposition or one source depositions here. Just to give you a microstructure of comparison of two type of microstructure of the perovskite surface. This is this one is the solution process. You can see the crystals are relatively larger for MFPBI3. After addition, the perovskite grains became smaller. This is cesium Fa, and this is tin-based perovskite. And if you will do evaporation of the perovskite, I think the perovskite grains are even smaller than that one, are much smaller. So much smaller grains we see is like than the VOC. The losses will be higher in much smaller grains. When we started to work in 2012 with the perovskite, our grain size were very small because that time we were working with only methylammonium lead triiodide. But after working for almost 10 years, we have worked approach different kind of composition engineering, which are different type of solvent engineering approach to make our crystal larger. Now we have even larger crystal of more than 1 micron size of crystals. Even we have it, much larger crystal we have it, and now we have it. And why we do it? Because methyl ammonium iodide, if you take, absorb till 780, and iodide has and this is a band gap of 1.54 electron volt. But if you take formaldehyde, it absorbs till 820 or 800. So if you will absorb higher, if it can shift the absorption onset to a higher wavelength, we can absorb more light. If we can absorb more light, we can generate more current. Similarly, if you replace some iodine with bromide, the band gap will increase. If the band gap will increase, we will have a higher VOC. So by playing with all these things, people come with different type of strategies. And the mixed perovskite, people were very happy that we have a higher performance. But now the community, after working, realized that this is very good, but it's also a double-edged sword because after some time there is a phase separation because we are mixing two halide. The halide gets shifted, gets separated, and the device performance is lower. It's just a symbolic here that how from methyl ammonium to mixed perovskite the performance increases here. So if the photovoltaic, I think there are some good phenomena and kinetics. Some is desirable, some is undesirable process. So what we do is desirable process is good, you want to push it. Undesirable process, we have to minimize it to minimize our losses. And what we want is we want separation of charges and we want extraction of charges. What we don't want is recombinations. We don't want electron and hole to recombine. We don't want high resistance to the contact. That's why interface is very important. And this is what we look at is the perovskite here. If you see the full arrow is the desirable process, means the holes will eject from valence band to conduction band, sorry. Charges, they go to the conduction band here. But there's also undesirable processes with dotted lines. Sometimes they come back, they recombine, and this is the losses here. So these things you can improve by designing new materials, with aligning the energy level, by passivation approach, and energy level of the electron and hole transport material. These things you can minimize to a larger extent. So to improve the VOC, basically, by doing so, we will increase the VOC. VOC is open circuit voltage of the devices. And for this, we have to design energy levels. We have to design the energy level of charge selective contact. We have to define the effective control of the interface, orientation of the layering of the molecule, how they orientate, is the parallel or perpendicular directions. If we do passivation, we have to be defect. Yeah, we have to put tracks which can check the charge selective contacts. And these things we and electrical parameters of charge transfer, high mobility and conductivity, and surface properties, the grain size and defects of the perovskite. These are all things for today here. As I said about the mixed perovskite, everybody was very happy, but we saw that when we put light, they are very mixed, but when they come in the dark, they are good. When the light, sometimes they're mixing, demixing of the halide, and they form kettles of halide will be together, bromide will be together, and there are sometimes phase separation, and it's not good. And a very good article was also published by some people. They find with different techniques how the phase separation is occurring and how they are sticking together. There's another one factor we call for the perovskite, the tolerance factors, how to increase this stability. So we found the tetragonal, trigonal, cubic tolerance factor of the perovskite is close to 1, then you have a higher stability. You can be achieved. So methyl ammonium is not good, but if you take formaldinium has a tolerance factor of close to 1. That's why it's more stable here. I will show you some example of formaldinium, delta FAPBI3. We are working on a powder processing method. It's a pre-synthesized powder. So this is a fully solution. Just you put any solvent in that one. It is like a semiconductor ink, and you can deposit it. So we have developed this powder. It's the pre-synthesized perovskite powder, delta FAPI. And you heat them, it became alpha FAPBI3. And also we saw that the performance of the devices, we have measured it in close to 16% to 18% performance. We have achieved it. And the good thing is that if we have the pre-synthesized perovskite, so there will be no unreacted lead, because in the normal route, what we do, we take lead iodide and we take methyl ammonium iodide, we react them. So some of the lead iodide is unreacted. In this way, there's no unreacted lead iodide is there, and this is a good approach we are adopting. Almost of the people, the community is also adopting. This is the crystal, if you will, and the crystal size of 80 degree also they convert it very good crystal. At 150, they even go to a large crystals. Yeah. So when we did from delta FAPI3, we now working on an alpha FAPI3 powder, and we now found this is relatively more stable, because when we make them the powder thing, we heat them and then it converts to a delta phase, sorry, alpha phase. So if you select the conventional what most people were doing, FAPBI3, it's dark, it absorbs light, but after 24 hours and 100 hours, it became yellow or transparent. So it will not absorb light, it will not be good for solar cells. Delta FAPI is also good for 24 hours, then it's so slowly. So now we are working on alpha FAPI. You can see it remains black for 100 hours even in an open atmosphere. So it's black, it means absorb light, it can work for solar cells. And we also give thermal exposure at 80 degrees centigrade, and alpha FAPI remains also color here. So it will be working. And there's no change in the absorption in all these three, because this is the intrinsic properties of the material. The absorption is not shifting. The FAPIs go to a 20, a 25. But there's an ordering by powder processing. There's an ordering of material, and the ordering of material is, we can see the microstain is decreasing with the alpha FAPI. So the materials become more tolerant to the environmental attack. And the Urbach energy also, if the microstain will decrease, the Urbach energy will decrease and the VOC will increase. So if we haven't done it, and then we also put additive engineering, means ionic liquids are very hydrophobic or fluorinated molecules. So we put some of the high fluorinated molecule in that. We can see ordering of the crystal is more than a perfect here. This also push our performance. And we have measured also very good stability of by putting this additive engineering. And why it happened, if you look at the surface properties, the contact angle is measured, it's 92 degrees, and it improves to 100 degrees. I mean, surface became more water repelling properties. Surface is showing more water repelling properties. Means you cannot attack environmental identity. So the red part you can see is the stability here. This is JV curve, and this is the EQ graph in how many photons are converted into electrons. So it's almost 85% in the visible region from 400 to 800. It convert there. We also we monitored the stability at 85 degrees centigrade for 500 hours, and it was relatively stable. You can see that there. And this is the most of the people also now they realize that MAPBI3, the first we have been working on, is not stable enough because they change phase from one phase to another at 80 degrees centigrade. And FA is more stable. So now the community is a big push to the FAPBI3 because this is also tolerance factor is high. And there was a paper last year in Nature which reported almost 25.6% with the use of formaldinium FAPBI3 because this is methyl ammonium. When you put one CH2 group extra, it becomes formaldinium. So this is the same configuration they are using NIPA structure, perovskite, a passivator, a spiro as a whole transport material goal, and they have achieved 25.6% efficiency. So without any passivations, the authors got 24%. With the red curve, you can see after putting the passivation in FAPBI3, the efficiency was increased. This is the EQ graph. And also show this material shows very good luminescence property. So a good solar cell should be show very high luminescence property also they have showed it. And the reference was almost 24%, but by doing this passivation of FAPBI3, 25.6% has been reported by last year from in a Nature article. The VOC is also 1.18 or 1.19, whatever you say that, and VOC. So these are very good approaches to increase the performance, high performance cells. This recently published article, I think this is because most of the people you think that we have a lead iodide in our material. So lead is environmentally banned material. But the amount of lead, let me tell you, is much lower than what we use in silicon in the soldering or with the car batteries, 1,000 times higher. But silicons, we are much less than the silicon which you use in soldering. But then most of the people, the community is also working on reducing the amount of the lead. So if you can have a mixture of lead and tin. Tin as such is not possible because of tin plus 2 oxidize very fast to tin plus 4. So if you make a mixture of lead and tin, and so this is also very good, and they have band gap of very close to 1.2 electron volt. If you 1.2 electron volt of the band gap with the lead and tin, you can achieve by if you could do 50-50 lead and tin with formaldinium and methyl ammonium. So these people have also achieved almost efficiency of by doing so 22.23%. But what we did, what they did is that they used, because the band gap was very low for 1 and 2, this is very 1.1 or 1.2 is very good for tandem approach. So you can have a perovskite tandem. So other perovskite which has a high band gap like methyl ammonium bromide based, so they found a new composition which has a band gap of 1.8 electron volt. So they put wide band gap, narrow band gap perovskite as the lead and tin at the top, and wide band gap perovskite of 1.8 electron volt at the bottom. And they have achieved recently 26.8%, 26.7% efficiency by doing so a tandem of perovskite. So this is also a very good approach to increase to performance of the solar cells. They played different thickness here, and the narrow band gap perovskite, you can see they go up to 200 nanometer of the thickness. And this is a large area they fabricated what they call 1 centimeter, 2 centimeter, which give you 22%, 22.5% efficiency. So this is the perovskite tandem, which is a company called Oxford PV, which is working on silicon and perovskite tandem, which is also close to 30% efficiency. They have reported it. Now I want to introduce, I said perovskite is very large crystals and very highly polar. So interface is also important. And there's a very famous saying from this this gentleman who won a Nobel Prize: the interface is the device. Interface is the heart of any devices. So if you can master the interface, you can master the device performance. So basically, to increase the stability and align the band alignment, we have used 2D material. The 2D material, like not graphene, other than graphene, there are plenty of them: MOS2, WS2, and different type of 2D material we have used. We have placed a very thin layer of 5 to 10 nanometer of MS2 here between the whole transport material and perovskite. So this will also protect the perovskite from environmental attack, or improve the stability and align the energy level. You can see the energy level is aligned and the VOC is increased. A very good, more almost 180 or 190 electron volt VOC increases, and we achieve close to 18% efficiency. And this is a very good efficiency performance because we have used PTA, polytriarylamine, which is more stable, and it was undoped. So undoped HTM with this is a very good efficiency we have to put it. This is the cross-sectional of a cross-sectional SEM images of a devices. You see the 10 oxide is very thin layer, 100 nanometer, perovskite is 400 nanometer. MOS2 and PTA is almost close to, we cannot see MOS2 because it's only very thin layer, 110 nanometer, and PTA is 50 to 60 nanometer. This is the cross-section of the devices. So without MOS2, the devices give 15, and with MOS2, we can go to 18% efficiency. This we can escape. We characterize some electrical parameter why it happens. So we found the built-in potential was higher, the defect was lower, and the trap density was lower, and that's why device came. But the good thing is that you can see the rate of the device stability was much higher than that one. Similarly, we introduce another 2D material like WS2 here. There's a cover of the journal here, a very thin layer WS2 as the interfacial layer with the perovskite is also increase the voltage of the devices and stability, increase the voltage of the devices and the performance here. They also align the energy level of the devices. I can escape before. We did a lot of electrical characterization to understand why it's happened. So built-in potential higher, and we also found that this be effective in the photosaturation is achieved at very low voltage by placing this 2D material, and the device is also more stable here. Recently, we have been working on these are the inner 2D materials because they have no functional group. Now we are working on the functional 2D material like carbon nitride. So here we have an amine group here, and this amine group will also passivate the perovskite and will also this carbon nitride is as an interlayer here. So different type of two type of carbon nitrides, both are C3 but different synthesized for different synthesis processes, solid state and liquid state, and both have a different color, so there's different band gap, and we found one of them is good here, which improve the performance stability to be very high state, and we close almost to 20% efficiency we have achieved with this one. And the good thing is that a 500 hour of maximum power point tracking, the device is losing some of them, but it is still, they are unencapsulated devices. If you encapsulate them, they will show even a higher performance, higher stability, they can do that. And BIPV as a semi-transparent solar cell is also very important. If you can decrease the thickness of this perovskite to 100 nanometers instead of going for high efficiency, and we will put some polymer matrix to bind it, we can see almost transparent perovskite solar cells we have achieved, and it shows you efficiency of 11% to 12% efficiency. As I said, the perovskite, and then we have a different type of material, N-type and P-type. N-type is more subtle, but P-type is a more active role in that. But P-type is material we put to extract the charge efficiently. And then it's the white choice. Generally, we take from a Spiro, but a Spiro we buy from markets, they're very costly, and also it's not UV stable. So in the long term, either like nickel oxide or graphene oxide, copper iodide, or some small molecule like PTA, PTST, other type of organic materials need to be developed, which are more stable. There are some requirement that the energy level should be matching with this energy level of the perovskite band alignment. There should be high mobility. High mobility, there should be no phase transition, because if there is a phase transition at less than 100 degrees centigrade, the solar cell will not perform very well in high humidity temperature, and this will be dissolved in orthogonal solvent. So my group has also reported, yeah, as I told, they have been high cost of the Spiro, they have reduced the stability, and also Spiro need doping, and because I need to oxidation, it needs lithium salt doping. Lithium salt is highly hygroscopic. We need TVP to increase the, so all these things increase the recombination, etc. So we are trying to get rid of all this dopant and trying to develop a new type of HTM, trying to develop HTM which are dopant free, so that we will not compromise on long-term stability. And we have been successful in doing so. This is just one example of pyridine bridge diphenyl carbazole. Carbazole is a very good organic semiconductor material with mobility. And with pyridine will be, you know, they will passivate the perovskite surface. And only with pyridine, the thin film were not uniform. When you put carbazole, the electrical properties improve, and also thin film, the uniformity of deposited film was increases. And the performance showed close performance to the Spiro, but the Spiro was 400 euro per gram. By this material is almost less than 30 euro per gram. We have calculated it, and there's no hysteresis and stability also. Similarly, we took another is like phenothiazine core. Phenothiazine core is a very low cost core here, but it's more robust. It's a very simple process. We use one-step process to synthesize this phenothiazine core. It was more air and thermal stable. It's a robust and is a very good optoelectrical properties. This is the phenothiazine core. So different type of organic semiconductor we use it to increase it. Then one thing is that recently we have been working on a fluorinated HTM, because fluorine, is Teflon which you use in your kitchen utensil. It repel water, it repel oil. So similarly, we use fluorinated HTM, organic molecular HTM. So they will be also working very well to boost the stability of this material here. This is the PL quenching. They say this fluorinated very well, quench the perovskite, cool down. They would use 2 of them. Without fluorine, they form big crystals, and there were no uniform deposition. But with fluorine, there's a uniform deposition. It forms very good uniform layer. And in dopant state, without any doping, it shows very good performance. And this way, stability was improved. So we published it. We also played with nickel oxide, the inorganic HTM, to increase the stability. This is the nickel oxide as such. We put a very thin layer of organic material here, organic semiconductors. It fills all this to form a uniform thin film of nickel oxide. And it gives a very good performance, and stability is a very good stability with nickel oxide and with organic HTMs here. So it's a bilayer of HTM, very thin layer of organic, and 50 nanometer of nickel oxide. And also you can see the perovskite crystals are larger, because perovskite crystals, you grow them on your HTM in case of PIN structure. So the perovskite grains deposit on that one. So device also showed very good reproducibility with the DNA. All things, I think with this, I like to stop here. My time has also come here, and I don't want to take you more time. So we can say thin film technology is ready to take off. We have 2 things very good, like cost and efficiency. The missing is the stability, which have been also improved in the last 5 years. Most of the people are working. Perovskite is a blockbuster thin film technology. We have to look for a thin film technology. Why it happened? Because we use very low amount of materials, and it also put aesthetic benefit. By doing molecular chemistry and designing a molecular engineering of material, we can design different type of semiconductor materials for put as a charge selective layer for p-type as a p-type material. So we call them our next generation materials. This p-type, what I talked about, they are not only good for solar cells, they are good for LEDs, different type of sensors, because they are semiconductors at the end of the day. So you can we use them. And then we have it, we are developing this eco-friendly high performance functional material, which is addressing UN sustainability goals here. And these materials will be UN sustainability goal addressed by developing new photovoltaic technology, by developing new energy based devising new materials. What we showed that we played from electrical properties to optical properties to system engineering, crystal engineering, and to the device level. And this is what whole value chain we work on. What is the biggest challenge is the price competition, because the price of silicon is going down, so it doesn't allow any new technology to enter into the market. And we need for government support. Maybe silicon has a 25-year lifetime, but maybe a new solar cell which will be very cheap and with very low environmental impact. Can work for 5 years. This is also very good. So this type of policy change we needed. I think with this, I like to thank you. I like my funding agency, European Research Councils, Spanish Ministry, the Basque government, European other agencies funding my research. And I like to stop here. and be more than happy to answer your question. And I will leave you with my quote: that future is electric, either for storage or for generation. Thank you, Paula. And emission anywhere is a threat to humanity everywhere. We cannot afford that. Only undeveloped countries should. We cannot go open their factory there. It will also come back to us. So emission anywhere is a threat to humanity everywhere. So we have to be use less carbon footprint to be more renewable product using. Thank you, Paula.
Hello, Shahzada. Thank you very much for your presentation. Really interesting, about all the evolution of the technology and this type of obviously of materials that we are starting using more and more because of, as you can see from the on the screen, future is electric, and we need to adapt and try to obviously reduce the different types of emissions that we release to the atmosphere and to the environment. So I think it's really interesting, the presentation that you gave us, as I said, with all the insights about the evolutions of this technology and the prospects of future growth, the same as from this material. So thank you very much again for your presentation and your time. The problem with the questions, as we normally will do, we normally will give like extra 10 minutes after the presentation, but because we have overpassed like the time that is allocated for this type of webinars, we don't want to normally like do it maybe like a tiny bit too long, because as we all know, like we want to make the difference, like trying to only base in a half an hour, like 40 minutes stops like webinar. So anyways, as you said, like if there is any questions or
I'll leave you my email address on the first slide.
Yeah.
You can write to me. I'm more than happy to answer it.
Yeah, so that's what I was gonna tell like the audience, you know, at the end, that if you have any questions or any type of like topic that you would like to discuss with Dr. Ahmad, like just please like either send it directly to him or get in touch with us in Fotoplat, fotoplat@fotoplat.org. Cualquiera que tenga preguntas adicionales para el ponente, por favor, podéis enviárnoslas o bien directamente al ponente, como he dicho, o bien a través de la plataforma. Again, I'm gonna close. I'm really sad to close, but like I have to. Just try to stick like to times, as I said before. So again, thank you very much. Muchísimas gracias, doctor Ahmad. Increíble presentación, la verdad, como he dicho, muy interesante todos los temas que nos estabas comentando, la verdad. Y nada, solamente quiero recordar también a todos los presentes, like I would like to remind you, like the next webinar, el siguiente webinar que vamos a tener desde la plataforma, tendrá lugar el jueves, no miércoles, 19 de mayo. En el horario de siempre, 4 y media, y esta vez vamos a contar pues con Onyx Solar, que nos va a contar un poco sobre el BIPV, la integración de la fotovoltaica en la edificación, con una ponencia pues bueno, titulada BIPV as Key Material for Green Building. Esta ponencia no va a ser en inglés, en teoría, pero bueno, justamente una de las aplicaciones, one of the applications of Perovskites is like a BIPV, and like like with the different like characteristics of like this type of material, like you can make really flexible modules and really flexible cells at the end. So you can really like apply them like to these different like applications, as I said, like BIPV, that is like the topic of the webinar that is going to be next like in 3 weeks time. So again, thank you very much. Muchísimas gracias a todos los que habéis estado con nosotros. Os esperamos de nuevo, os digo, el 19 de mayo. Tenéis toda la información de todas maneras en la descripción de este mismo webinar, cómo podéis apuntaros, cómo podéis enviar mensajes a Fotoplat también, por si acaso hay ponencias que proponer a la plataforma o ponentes que proponer, porque los temas bastante son interesantes, and solar energy is the future, and like everyone is talking about it, you know. So like if you have any topics, like I'm talking to everyone, if you have any topics that you would find interesting, like to cover during like these sessions, please just let us know, and we will analyze the opportunity, like the possibilities of this happening. So again, thank you very much for your time. Keep saying it, but have a really nice afternoon, everyone, and hope to see you another time.
Thank you.